Okay, thanks everyone for tuning in to a new online seminar. Today we're very happy to have Christiana Pantelidou from Trinity College Dublin, who's going to tell us about gravitational turbulence and large D. So please, Christiana, take it away.
Thank you very much for the introduction. So let me start by thanking you for inviting me to speak on this online seminar series, and also thank all of you for actually tuning in for the seminar. So today, my main goal is essentially to keep you away from reading the news about the coronavirus for about an hour or so. I've been struggling with this over the last couple of weeks, and I guess some of you may as well. So this will be a great, hopefully a great way to spend the next hour, when I'll try to tell you a bit about some interesting physics related to gravitational turbulence in the large D limit of general relativity. This is based on some recent work that we published in collaboration with Tomás Andrade at the University of Barcelona, Julian Sonner at the University of Geneva, and Ben Withers at Southampton University. So let me jump right in. So as some of you listening to this talk may very well know, the idea of gravitational turbulence is not something new. There are a few papers published on the topic, mainly from 2012, 13, and 14 from the Perimeter Institute group. And what we're looking to do here is essentially to revive that line of research and extend it, but from a slightly different point of view. And the reason why we want to do this, and we want to do this now, is because we believe that studies of gravitational turbulence are particularly timely at the moment, especially given the recent experimental observations of black hole mergers, thanks to the LIGO collaboration. So such black hole mergers essentially give us a window to the nonlinear dynamics of gravity. And as such, they're an ideal arena for us to look for new physics, and in particular for the physics of gravitational turbulence. And let me elaborate a bit on this. So as you all very well know, black hole mergers have three stages. At very early times, we have the in-spiral phase, when essentially the two black holes orbit around each other. And this is very well captured by post-Newtonian physics. On the other extreme, at very late times, we have the ring down of the final state black hole. And this is very well captured by the Kerr solution, plus a handful of long-lived quasi-normal modes. And in both early times and late times, we have a very good control of what's going on. Now, in intermediate time scales, like roughly around here, where the actual merger takes place, the nonlinear dynamics of gravity become important. And this is precisely why one might expect to see an imprint of gravitational turbulence in this regime. But why is this the case? In order to answer this question, let me take you all the way to a completely different field, that of fluid mechanics and the Navier-Stokes equations in particular. So Navier-Stokes are the equations that govern the dynamics of the fluid velocity, and they have been studied in the context of turbulence for roughly about a century now. Okay, and essentially what people concluded through these studies is that turbulence is actually rooted in the nonlinear structure of these equations. It's these nonlinear structures that actually give rise to the energy cascades across scales. And here I mean both the direct and the inverse cascade, depending on how many dimensions you are. And it's this cascade that actually led to the washout of the memory of how we actually entered this turbulent regime. And by this, I mean either initial data or the details of the forcing term, of the forcing that you're doing on your system. And it's precisely because of this washout that one ends up with universal dynamics. Okay, so at this stage, what we have is the following. We know that in fluid mechanics, turbulence is a result of nonlinearities. On the other hand, we have that gravity is a nonlinear theory. So it's just simply natural to ask whether gravity possesses a turbulent regime itself. Okay, and in fact, there are many reasons to believe that this should be the case. Here I'm just highlighting three. There are many more, but essentially all of them boil down to the fact that black holes and event horizons in particular can behave like fluids. Okay, so to remind you, in the 80s, we had the membrane paradigm, where the black hole horizon was essentially treated as a viscous fluid. Then in the early 2000s, we had the works by Gofton and Staronets, where they computed the transport properties of horizons, and in particular the shear viscosity to entropy density ratio. And then a few years later, we had the fluid gravity correspondence, where a fluid living on the boundary of finite de Sitter spacetime was related to a black hole living in the bulk of ADS in a way that involved a derivative expansion. Okay, so the aim of this talk is to actually go and collect direct evidence for the existence of this gravitational turbulent regime. And what I mean by this is we want to go and explicitly solve Einstein's equations to construct black hole solutions that obey Kolmogorov's theory of turbulence. This is the aim. But before I move on to tell you precisely how we construct these black holes, let me just refresh your memory about Kolmogorov's theory. Okay. So Kolmogorov published his theory in 2 seminal papers in 1941, and this is precisely the reason why this theory is sometimes referred to as K41. Okay. And in his theory, he focused mainly on Navier-Stokes equations in 3+1 dimensions. And at the time he was working on this, it was clear to everyone that was working on turbulence that one should not think in terms of the velocity field, because the velocity field becomes in a stochastic way. Instead, one should think in terms of the statistical properties of this velocity field, like, for example, the probability distribution function, or PDF, because such statistical properties are actually reproducible and have a simple structure. Okay? But unfortunately, it was soon realized that the statistical evolution equations are unclosed. What this means is that you have more statistical properties that are unknown than number of equations. Okay, and this is essentially what hinted towards the need to make further assumptions. And this is precisely what Kolmogorov did in 1941. So he made 3 hypotheses: the isotropy hypothesis and 2 similarity hypotheses, and this is what these were about. So the first one essentially said that if you're dealing with scales that are smaller than the scale of your sample or the scale of your grid, if you're doing numerical simulations, then at those scales, the turbulent motion becomes statistically homogeneous and isotropic. So in terms of the probability distribution function, or PDF for short, this means that this quantity becomes translation and rotation invariant. Okay, this is the isotropy hypothesis. And then the first of the similarity hypothesis states that if you're dealing at the same scales as before, then the statistics take a universal form. And in fact, the physics can only depend on 2 scales. One is the viscosity, which I denote here by V, and the other one is the kinetic energy transfer rate, which I denote by epsilon. And essentially, this epsilon essentially tells you how large vortices in 3+1 dimensions break up into smaller ones. Okay, so the content of this similarity hypothesis is essentially that the PDF should only depend on the velocity, on the viscosity, and on epsilon. And then the last of the hypothesis says that actually the viscosity, the effects of viscosity set in only at much smaller scales than what we were discussing earlier. And essentially what this means is that there is a range of scales where the PDF actually depends only on epsilon and not on the viscosity. Okay, so these are the 3 hypotheses that Kolmogorov made. And having this in mind, he went on to consider the following 2 observables. On the one hand, he was interested in endpoint functions of the velocity field in position space, but he wasn't interested in any such correlations. In fact, he focused on the so-called longitudinal structure functions, which here I denote by Sn. So the way to compute this is the following. You take the velocity at some point P1, and then you take the velocity at some other point P2. You take the difference, you dot that with the unit vector connecting the 2 points, and then you raise this to the power n because you're interested in the nth longitudinal structure function, and then you take appropriate statistical averages over realizations because you want to extract the statistical properties of this function. But remember that we are working under the isotropy hypothesis, and essentially what this means is that this function here should only depend on the distance between the 2 points involved in the calculation, which, and I denote this by r. Okay, so this was one of the observables that he considered. The other one was the kinetic energy power spectrum. So when it came to S2, the second longitudinal structure function, it's actually more common to think about that in terms of momentum space. And this is roughly what this quantity here is. So the kinetic energy power spectrum essentially measures the amount of kinetic energy that you have in a shell of radius k in momentum space. Okay, so these are the two observables that he focused. And having in mind this and also the hypothesis from the previous slide, this is what he came up with for the phenomenology of turbulence in 3+1 dimensions. Namely, he said that one should see a direct energy cascade, which in terms of the kinetic energy power spectrum in momentum space on a log-log scale, it should look something like this. But let's take things step by step. So let's imagine that we have our sample, and at some time t = 0, we inject a few vortices of a certain scale. Now, because of the nonlinearities of Navier-Stokes equations in 3+1 dimensions, these vortices will start breaking up. They will break to smaller scales in position space, and those vortices will break to even smaller ones and smaller ones until we reach the scale where dissipation becomes important, and then those vortices will essentially be removed from the system. Okay, so we see that we have some transfer from a certain scale to smaller ones, but at the end, everything is dissipated away. This is decaying turbulence. Okay. On the other, but how can we actually see a picture like this one here? Now, the way to go is to actually continuously pump vortices of a fixed size into the system. When you do that, then those, when you continuously inject vortices into the system, then those will continuously break to smaller ones, and those will break into smaller ones in a self-similar way, giving rise to an inertial range where the energy is transferred across scales at a constant rate, epsilon. And this is precisely the similarity hypothesis that we saw earlier. So now, as the system is populated with smaller and smaller vortices, this inertial range that we see developing here will actually extend. Remember that here we are in momentum space, so it will extend to larger and larger values of k, so smaller scales in position space, until it hits the dissipation scale and it cannot extend any further. Okay, so essentially what we have here, we keep pumping in vortices at this forcing scale here, then energy is transferred to smaller and smaller smaller and smaller scales, or equivalently at larger values of k, and then the vortices are being removed here because of the viscosity. So our system goes into a steady state. And in particular, notice that in this inertial range here, this straight line, the kinetic energy power spectrum was predicted to scale like this, k to the minus 5/3. And this is precisely what the direct cascade is. You have your inertial range stretching more and more towards the right of this plot. Okay. Now, on the other hand, the phenomenology for turbulence in 2+1 dimensions is slightly different. In particular, one should see an inverse cascade and not a direct cascade, as we saw before. And here I'm plotting precisely the kinetic power spectrum as before in momentum space, again in log-log scale. And we see something slightly different. So once again, just like before, we have to keep forcing the system by introducing continuously vortices. And this is what I'm doing here, where you see this peak. This is the forcing scale. But now, because of the nonlinearities of Navier-Stokes equations in 2+1 dimensions, these vortices will not split, but instead they will start merging with each other. So in the same way as before, we'll now see the emergence of an inertial range that will, as time evolves, it will stretch further and further and further towards the left of this image. Okay. And this is precisely what the inverse cascade is. And once again, Kolmogorov logic predicted that the kinetic energy power spectrum should behave like this, k to the minus 5/3. And if the system was infinite in size, this would be the end of it. So this line would extend all the way. But for any practical purposes, this is never true. If we have a sample in the lab that has a finite size, if we're doing a simulation, then we have a finite size grid. So at some point, it's inevitable that we'll hit the IR effects. And what precisely happens there, it depends on precisely what you do. So what I will show in the simulations later on, we will be working at finite volume. This is our approach. The more standard thing to do from hydro simulations is to add instead friction terms to remove this large scale vortices. Okay. And
so Christiana, a question online. Well, actually, all the questions are online these days. Is shear viscosity playing any role in for 2+1? Probably not, right? Or not much?
No, it's further on the other side.
Okay. Yeah, thanks.
Okay. Yes. So also on this plot, you can see this direct cascades. That's cascade towards a higher value of k. But in this talk, I will completely discard this because it's not as universal as the k to the minus 5/3 inertial range. Okay, we'll just ignore that. Okay. Now, as you've seen on this plot and also on this plot, in the inertial range, the power law was always k to the minus 5/3. And actually, it turns out that that is true in any number of dimensions, and you may wonder why. And the answer to this question is that it's simply based on a dimensional analysis argument. And because this argument is quite neat and short, I'd like to walk you through it. So if you remember, the last of the similarity hypothesis said that the physics in the inertial range should only depend on this epsilon, which was the kinetic energy transfer rate. So it has units kinetic energy over time. So length square over t to the cube, okay? But if the physics, and in particular the two observables that we're interested in, can only depend on this, then we should make up the dimensions using only epsilon and some length scales. And this is precisely what I'm doing here. So the kinetic energy power spectrum has units length to the cube over time square. Okay, so if we first take care of these time dimensions, it means that this quantity should be proportional to epsilon to the 2/3. And then we simply make up the remaining of the length dimensions using k, which is remember this quantity is defined in momentum space, so this is the wave number. And it turns out that the power should be k to the -5/3. This is precisely what we saw earlier. Now we can do the same for the structure function. This has units length to the n over time to the n. So treating first the time dimensions, it means that this should be proportional to epsilon to the n over 3. And then since this quantity depends also on the distance between the 2 points used to construct it, which here denoted by r, we should use this to make up the remaining space dimensions. So the power should be r to the n over 3. So these two are the famous Kolmogorov power laws, respectively for the power spectrum and for the nth longitudinal structure function. And later on, when I'll be constructing the black holes and I will want to check whether I have turbulence or not, this is precisely what I will be checking. Okay.
Another question. So if you're talking about the relativistic system in which you also have speed of light, which allows you to, which gives you like L and T, I mean L over T. Does this analysis hold straightforwardly, or?
So I should say that here we are dealing with non-relativistic.
No, sure, yeah, I know.
So this was not a problem. Now, how it works in the relativistic system, I'm actually not sure. That's a good point. Yeah, I don't know. That's a fair point.
Okay, maybe we can have a discussion with more people after you're done.
Yeah, sure. Okay, so with this, I essentially finish my introduction. So let me recapitulate what the plan for the talk is. So here we want to construct turbulent black holes in general relativity. And we want to check that these black holes exhibit a universal regime. And then we want to go and test that this universal regime is actually compatible with Kolmogorov's K41 theory. Okay, of course, this problem is tremendously difficult from a technical point of view. We have no symmetries in the problem, which means that all the components of the metric will be turned on and they will depend on all the directions. So this is a very demanding problem computationally. But this is not the only issue. When we are doing things in purely on the gravity side and we'll lose this connection with the fluid variables, it's not very clear what quantities we should plot in order to look for the power laws that I showed earlier. Okay, so our approach here is to essentially try and simplify the problem as much as we can. So we will solve Einstein's equations, but we will consider planar horizons. We will consider asymptotically ADS spacetimes. And this actually buys us some connection with fluids, but it's not enough. And in order to simplify things a bit more, we will take advantage of the large D limit. Essentially, what one does here is to treat the number of dimensions as a parameter in the theory and do a perturbative expansion in 1 over the number of dimensions as this D goes to infinity. And this not only simplifies the dynamics tremendously, but it also buys us this connection between the metric components and the fluid variables. So this will be particularly useful. And then, as I said earlier, in order to see K41, we have to force the system continuously. So we we'll have to introduce a forcing term in our Einstein's equations. And when we do that, we need to do it in a particular way to respect the isotropy hypothesis. Okay. So this is the plan. And let me first start by giving you some more details about the large D limit. Okay. So the large D limit became quite popular in the last 5 or 6 years, I think, mainly due to the efforts of Roberto Emparan, who I think is listening, and his collaborators, and also Shiraz Minwala and his collaborators. And essentially, the main idea is to treat, as I said on the previous slide, treat D, the number of dimensions, as a parameter, and do perturbation theory in 1/D as D goes to infinity. And it turns out that this is extremely useful when one is dealing with black holes. Essentially, the dynamics simplify tremendously. And I'll give 2 arguments why this is the case, but essentially both arguments essentially boil down to the same thing. So imagine that we have a black hole, and then there are 2 scales that appear in the problem. One is the radius of the horizon, R0, and the other one is R0 over the number of dimensions, over D. So as D goes to infinity, we see that there is a separation of scales here. And whenever there is such a separation of scales, this hints towards the existence of an effective theory. And in fact, this effective theory captures the universal dynamics close to the horizon. Okay, so this is the main idea, but let me now give you the 2 arguments that I promised. So the first argument has to do with the localization of the gravitational potential. So if we consider the simplest black brane solution in ADS, then that's the Schwarzschild ADS, and it's effectively given by the blankening factor that I write here, F. So R is the radius of is the radial direction in ADS, and here in this coordinates, the boundary is located at R going to infinity. R0, just like before, is the radius of the horizon. We see that when R is equal to R0, F is equal to 0, as it should at the horizon. But then we also have one more parameter, this D, which is the number of space-time dimensions on the boundary of ADS. Okay, and on this figure here, I plot precisely this unblankening factor as a function of R for 2 cases. In this case, I picked D equal to 3, so we are in asymptotically ADS 4. And in this case, I think I picked D equal to 10. So the point is that this is much larger than 3. Okay. So we see that at very large values of R, this blankening factor goes to 1. This is essentially what one expects when we are in an asymptotically ADS spacetime. But when we zoom in close to the horizon, the 2 cases behave quite differently. So in particular, in this case, we see that the gravitational potential becomes very localized in a very thin stripe of width R0 over D right outside the horizon. On the other hand, in this case, at finite D, there is no such localization of the gravitational potential. So this extends in principle to scales of order R0. Okay, so here, once again, we see the 2 scales that I showed on the previous slide. And as D becomes large, we see that there is a separation of scales. Now, if you do not want to think about the gravitational potential in these terms, you can instead think about the radial gradient. So in the case where D is large, we see that the radial gradient is very steep. So it's of order D. On the other hand, the transverse gradients are of order 1. So once again, you can see the separation of scales that way.
Sorry, by transverse gradient, do you mean like the gradient of the metric in the directions transverse?
Spatial, for example.
So you mean like, say, gxx derivative of this with respect to r?
Derivative with this, so I'm comparing derivative with respect to r and derivative with respect to x, where x is one of the spatial dimensions.
Okay, well, which in this case is 0.
Yes, in this case, yes.
Okay.
Okay, so this was the first argument that has to do with the localization of the potential. The next argument has to do with fluctuations. So the natural set of fluctuations to consider around this spatial ADS black brane is the quasi-normal mode spectrum. So what we do is we consider linearized fluctuations around this metric, and then we go and we solve the corresponding differential equations subject to ingoing boundary conditions at the horizon and sufficiently fast fall-off close to the ADS boundary. Okay, and when we do this computation at finite d, this is what we get. We get a spectrum of quasi-normal modes that is infinite but discrete. And in frequency space, the distance here is of the order of the temperature of the black hole. Okay. Now, on the other hand, if we take d to be infinite, then this spectrum here essentially splits into two sectors: the light sector with frequencies that are proportional to 1/r0, the radius of the horizon, and the heavy modes where the frequencies are proportional to d over the radius of the horizon. Okay, so once again, we see the appearance of the two scales that I mentioned earlier, and as d becomes big, we once again see the separation of scales. These modes become infinitely heavy. And what is natural to do from this point of view is essentially to integrate out these heavy modes in order to get an effective theory for this light degrees of freedom. Okay, and this is precisely what I'm going to tell you how to do on this slide here. So this is the procedure in order to construct large D effective theory. And this is just a sketch, but hopefully it contains enough information. So the starting point is our sparse-shelled black brane, which I showed earlier the Rankine factor. Here, more compactly, I denote the whole metric by G0, and it's a function of the radial direction in ADS. And then earlier, this also has a parameter, which is the radius of the horizon. But here, instead of that, I choose to think in terms of the energy density A. Okay. Now, since this is a black brane, I can simply go and do a boost, a Lorentz boost, in order to generate some momentum, which here I denote by pi. And at this stage, these two parameters are just constant. Okay. So the next step is to promote these two constants to actually have a dependence on t and x in this particular way. And then the new metric, G0, will depend not only on R, as we saw here, but also on T and X. And then we plug this into Einstein equations, and of course, they are not satisfied. But in a way, the order of the error is 1/d. Okay, so what we can do is go to the metric and add a correction that is proportional to 1/d. In this particular way, and then plug this into the Einstein equations and solve for the radial dependence of G1 in order for the Einstein's equations to be satisfied up to order 1/d squared. Okay, and following this process again and again, one can get the metric up to any order in 1/d in principle. Okay. So essentially what we've done here, we've solved the evolution Einstein equations, and what we are left is just the constraints, okay? And as the name suggests, the constraints do not depend on the radial direction, okay? And this is precisely what we get. We get these two equations, and one equation for the time evolution of the energy density, alpha, and one equation for the time evolution of the momentum, p. Okay, these equations look very much like Navier-Stokes, but they're not Navier-Stokes.
Sorry, and these constraints arise from the leading order, or they arise from all orders?
So you get, these are the leading order.
Okay.
Yes, in principle, you should repeat this process at every order.
Okay, thanks.
And this, this is just leading order in 1/d. Okay. So these equations, as I said, look very much like Navier-Stokes, but they're not. They're exact in gradients. And the nice thing about them is that because of this similarity with Navier-Stokes, they give us this link between the gravity computation and the fluid variables that we were missing so far. So this is very important. Okay, and now some comments are in order. Note that here we chose to restrict the dynamics of alpha and p in p+1 dimensions, while we assumed that these two quantities are translation invariant in the remaining spatial dimensions. And in particular, for the simulations that I'll show later on, we chose p to be equal to 2. So from the phenomenology of turbulence that we saw at the very beginning, we expect to see an inverse cascade. Okay. Now, these equations look very simple, and they do not depend on the radial direction because we've already solved for that. So in principle, if we solve this, we obtain the full black hole metric in ADS. Okay. And another point that I'd like to emphasize once again is that these equations are exact in gradients, and because of this reason, they're under better control than hydrodynamics. So what one does in hydrodynamics is to expand into gradients, and then, but unfortunately on a computer we cannot simulate an infinite number of equations. We have to truncate at some point. But when we do this truncation, we get unphysical features that manifest themselves either as non-causal evolution or as instabilities. And this is true for both relativistic and non-relativistic systems. And then what one does is you should go and modify your theory by hand to remove these unwanted features. Okay, so here we are not doing a hydrodynamic expansion. We are exact in gradients, so we don't need to worry about this. Okay. So in the next few slides, essentially, I'll show you some solutions of these equations. And the first and simplest thing to do is to just solve these equations, having in mind turbulence, but without introducing a forcing term. Okay. Just use initial conditions to induce turbulence.
So if the fluid is incompressible, I mean, like if this divergence of P is 0, then A obeys what, like a diffusion equation. So somehow like take this largely limit, put you in some non-relativistic regime, right? So like probably like this question about relativistic turbulence was irrelevant in the context of what you're doing.
So it is true that the system becomes non-relativistic. It's compressible though.
Yeah, sure. Yeah.
Yeah. Okay. But still, what you get out of this is black holes, fully back-reacted if you want, black holes, at leading order in 1 over d.
No, of course.
So that's okay. Okay, so the first thing to do is to solve these equations with unstable initial conditions. Okay, and this is precisely what Rosalie and Jerome and collaborators did. And I think Amos is listening, so if I say something incorrect, please correct me. So what they did 3 years ago, I believe, was to study decaying turbulence in precisely the same limit as we do in large D. And they studied both 2+1 and 3+1. But here I'll be mostly interested in 2+1. So let me focus on that. And they solved precisely the equations that I showed earlier. And they used just unstable initial conditions to induce the turbulence. And in particular, they use the so-called counterflow initial data, okay, which I write down here. So the energy density is just a constant. The momentum in x is equal to 0, and the momentum in the y has dependence on the x direction in this precise periodic way. And they solve these equations using a variety of methods, always at finite volume. So in 2 spatial dimensions, they were on a T2 torus. Okay, and while they were doing this computation, they were monitoring the vorticity, which I write down here, and also the power spectrum. And I'll show you we reproduced that simulation, and I'll show it to you on the next slide to convince yourself. But essentially, what they concluded was that they could not see clearly the emergence of the inertial range and the inverse cascade as was predicted by K41. Okay, and actually Chesler and Jaffe had done a very similar simulation, but in finite D and in particular in ADS4, and they pretty much reached the same conclusion. And the reason why they couldn't see the agreement with K41 was because of the lack of driving, essentially. Okay, so let me show you the simulation. So here on the background, this is my domain. So this is X and this is Y. Here I'm plotting the vorticity. Okay, so we see that the vorticity has no dependence on Y, but it depends periodically on X, and it's positive, negative, positive, etc., etc. Okay, and then here on the bottom right, what I have is the kinetic energy power spectrum on a log-log scale. Okay, and what you see here, the lines that you see here, are associated with this initial data, and we see that there is a peak, a very narrow peak here, which essentially corresponds to the width of these stripes that you see. And then there is also a blob at very small values of relatively small values of K. And essentially this corresponds to some random perturbations that we added to the initial data just to set turbulence, okay? And this—
Hi, Christiana, sorry, can I ask you a question? Hi, this is Nabil.
Hi, Nabil.
How is the energy related to P and A again, exactly?
What do you mean by that?
I think you might have shown this, but I think I missed it. Is the energy equal to A exactly, or is it A plus P square or something like that? Or?
Yes, actually, you haven't missed it. I just haven't showed it.
Oh, okay.
There's a relation between the fluid variables and what I'm calling here A and P, but I didn't show it.
Okay. Is it simple, the relationship between the energy and A
yeah,
and P?
it is fairly simple, yeah.
Okay.
Yeah, I should have included that.
Okay. Can you give some idea what it is exactly? It's just A, or is it more?
So the energy is precisely A.
Precisely A. Okay, great.
Yeah.
Thank you.
But it's not one-to-one for the momentum, for the velocity.
Great, thank you.
Okay, so I was about to show you this. And this line, so this once again is the kinetic energy power spectrum in momentum space on a log-log scale. I discussed these two lines. This line here essentially corresponds to Kolmogorov's prediction. This is a line at proportional to k to the -5/3. Okay, so remember, I'll play this twice. The first time, I advise that you focus on the vorticity that I show on the background, and then the second time, just focus on the power spectrum. Okay, so once again, here we have the Kane turbulence, and the initial conditions are unstable. So as soon as the simulation starts, we see the formation of vortices. These vortices, because of the nonlinearities in 2+1 dynamics, they merge together, forming bigger and bigger vortices. Okay, so we have some transfer of energy from small scales in momentum space to bigger scales, position space, to bigger scales in position space. Okay, so it's the opposite in momentum space. Okay, so now I'll play it again and focus on the power spectrum. No, wrong way. Okay, so we see that in accordance with what we see in the vorticity, we have power transferred towards smaller values of k, so bigger scales in position space, but we never see the formation of an inertial range where the power spectrum scales like k to the -5 that over time extends more and more towards the left. Okay, and effectively this is simply because there was no forcing in the system. Okay, and this is precisely what we did. We took the large D effective equations that we saw before, and we modified them to add a forcing term, Fi. And notice that here, yes?
Oh, sorry, I wanted to ask if, I don't know that you hear it, that I made it loud. The question is, can I think about this Fi as coming from coupling your theory to the background metric?
You are ahead a few slides. Can I postpone the question?
Yeah, sure.
Thank you. Okay, that was a very good question. So here, I'm constructing this Fi by hand, just to be clear. And so I'm putting it on the right-hand side of the evolution equation for Pi. So in particular, I do not source the energy density, but I source the momentum in a way that injects vorticities to the system. So this Fi is proportional to epsilon ij, that's the antisymmetric tensor in 2 dimensions, and times the gradient of a function f. And I construct f in the following way. Remember that the isotropy hypothesis is restricting us here. Okay, so in order to construct f, I'm choosing a scale in momentum space, and then I sum over all Fourier modes that lie along a circle of that scale k. Okay, and I add those Fourier modes with random amplitudes and random phases. Okay, so this way my Fi is isotropic. Okay, and since I'm forcing the system with an external force, I do not need to choose special initial conditions. In particular, I can start from simple thermal equilibrium. So my initial conditions are alpha equal to 2 and the momentum equal to 0. And once again, I solve this at finite volume, namely 2 torus, and I use 4th order Runge-Kutta time stepping for the time evolution, and I approximate spatial derivatives with 4th order finite difference. Okay, and this is the simulation that we get. Sorry, it was too fast. So once again, at the background, I'm plotting the vorticity. This is x and this is y. Here is once again the kinetic energy power spectrum on a log-log scale. Okay, So as soon as I let this go, we see the formation of very small vortices and antivortices, that's red and blue respectively. And as time passes, we see that these vortices start not merging, but moving in a coherent way together with the ones around them. And if we keep this simulation going, essentially at the end, we end up with just two coherent structures rotating in opposite directions. That's the vortex lattice. That's the final state we get. Okay. So once again, we see that we have energy being transferred from very small scales to larger and larger scales, as one would expect from an inverse cascade. And now I'll play it again to check the power spectrum. Okay, so here it is. Once again, this K here, let me point out that this is where we're doing the forcing. Okay, and if I let this go further, we see that we have a transfer of power towards the left. We have a clear inertial range, and as time passes, this inertial range stretches more and more towards the left of the plot, or equivalently to bigger and bigger scales in position space. Okay, so now on the right hand side of the peak here, you can see the direct cascade that I showed when I was talking about the phenomenology of 2+1 turbulence. So we do see something, but we didn't analyze it further. Okay, so this looks very promising for an inverse cascade, as we were expecting, but this is just one realization. Okay, so in principle, we said we are interested in statistical properties, so we have to construct many such realizations and then take averages. And this is precisely what we did. We constructed 256 such realizations, and this is what we ended up with. This is, once again, the kinetic energy power spectrum in momentum space on a log-log scale. And here I have four time slices, very early times, then later and later and even later. And this here is the position where the driving takes place. And the black lines are the Kolmogorov prediction, k to the -5/3. Here, just simply ignore the normalization, is just arbitrary for illustration purposes. Okay, so we see that at early times we have a clear inertial range, but quite small. Then as time passes, the inertial range gets bigger and bigger and even bigger. Okay, and this is precisely what we expect from an inverse cascade. Okay. And then not just this, but we also moved on to check the structure functions. And here I'm plotting S2 all the way down to S10. Once again on a log-log scale, where this axis here is the distance between the 2 points used to compute these quantities. And the black lines are Kolmogorov's predictions, and we see that we have a relatively good agreement. Obviously, it becomes less and less accurate as we go down or to higher value of n. But this is actually a quite remarkable agreement already. It's for more than, well, roughly a decade on the horizontal axis. Okay. So hopefully in the last 3 slides, I managed to convince you that the black holes that we have constructed do exhibit a universal regime that is compatible with Kolmogorov's predictions. Okay. But we already had a question about this. So some of you may be worried that when I added that forcing term, I did that by hand. So in principle, I wasn't actually solving Einstein's equations. So is it possible to see turbulence in a fully gravitational description? I think this is what the last question was about. And this is what I'll show you on the next slide. So here we choose to drive the system using a deformation of the boundary metric. And in fact, we will be using the asymptotic value of GTT, okay? But now you have changed your boundary condition problem in ADS, so you have to go back to the procedure that I showed for deriving the large D effective theory, and you have to repeat that process, okay? And we did this a few years back with Thomas and Ben, and what we found is that the equations are exactly the same as the ones that I showed before, but now the forcing term takes this particular form that I write down here. In particular, it's a gradient of a scalar. Okay, this is not great because this carries no vorticity. So we cannot use this forcing term in the same way as we did before. Okay, but nevertheless, one can get turbulence using this forcing term. One option is just to use this to steer your system around in the same way as you steer your cup of tea. Or you can do what I'm going to show on the next slide, which is to set your fluid to be on a uniform motion and then quench your boundary deformation, gamma t from 0 to some symmetric Gaussian profile at some fixed position at time t equals 0. Okay, so this is what we are going to do. But remember that this way of forcing the system is neither homogeneous nor isotropic. And on top of that, you're doing work on the system at just one point in time when you turn on the quench. So in principle, this is going to decay over time. So we do not expect to see the rules of K41 appearing here. But we nevertheless do see turbulence. And this is how the simulation looks. So here, this is X and this is Y. This is my domain once again. I'm plotting vorticity. So at t equals 0, this is, So at t equals 0, it's the vorticity is everywhere 0. And then I turn on this quench. And then what we see, effectively, when I turn on the quench, what I'm doing is like I'm putting a cylindrical deformation in the flow of my fluid. Okay, so what we expect to see is a turbulent wake forming on the back of this obstacle. And this is precisely what we see here. So we start, the fluid is moving from left to right. And as this is happening, we see the turbulent wake. The vortices are then being dragged by the fluid towards the right. And since I'm doing everything on a torus, the vortices at some stage, they will come back and start interacting with the other ones and so on. So in principle, this is a proof of concept that one can get turbulence in a purely gravitational setup. This is not compatible with K41, but it's nevertheless a fully gravitational construction. Okay. Okay. And with this, let me summarize and conclude. So what I've shown you today is that we have studied gravitational turbulence in the presence of an explicit homogeneous and isotropic forcing. And we saw the emergence of universality in this out of equilibrium black holes. And this universality was actually consistent with K41 at an astonishing degree. And we believe that this excellent agreement is because we did not allow for any intermittency in the system. And in order to do this computation, we employed the large D expansion. But crucially, things are a bit under better control than when one does hydrodynamics, because these equations are gradient exact. And by following this process, even though we are solving only the constraint equations, we do get full about reacted ADS black holes. Okay, so this was the first simulation that I showed. And then the second one, it was merely proof of concept. So we started a setup with an explicit gravitational source. And this gave rise to a tidally induced turbulent wake. Okay. And before I finish, let me just put this in a bit of a physical context. So this sort of simulations are important for strongly coupled matter, quark-gluon plasma, or certain condensed matter systems through the ADS-CFT correspondence. But they're also important, as I said in the motivation at the very beginning, they're important for purely gravitational setups, and in particular for the plunge dynamics of black holes and neutron star mergers. Okay, and now let me be very clear on this point. We are not claiming that what we did has direct relevance for mergers, because in principle, one has to do the computation at finite d, also at asymptotically flat spacetimes, and also with spherical horizons. So this is a very long way away. But also we need to better, when we are doing the computation in a fully gravitational setup at finite d, we also need to understand which geometric quantities we should look at, and what effectively what is the origin of these turbulent cascades in gravity. Okay, and with that, let me thank you and leave it there. Thank you. Thank you.
Okay, Christiana, thank you very much for this very interesting and clear talk. Are there more questions online? Remember that you're by default muted, so if you want to ask a question, unmute your mic and speak up.
Maybe I can start with a question. So because you considered a flow that involved only two spatial directions, you got the inverse cascade. Mm-hmm. But if you had included three spatial directions, you would got the cascade to the UV. Would this cascade be consistent with the large D, with keeping only the leading term in the large D expansion? In a sense, would you have viscous effects that would kill it? Or you would have some problems with singularities arising?
Okay, so let me try and answer this question. First of all, let me point out that these equations, if I restrict, let me go here. So if I restrict A and P to have dynamics in 2+1 dimensions or 3+1 dimensions, these equations will not change. Okay, it's just this I will run from 1 to 3 instead of 1 to 2 that I'm doing. Okay, and in principle, such simulations have been done in 3+1 dimensions. In this case, where there was no driving, and so the turbulence was induced by initial conditions. Okay, so Amos can correct me, but they did do the simulations. Okay, and in principle, in that case, one should expect to see a direct cascade as what I showed at the beginning. With including a forcing term, this has not been done.
Okay.
Have I answered?
Yes, I guess mostly. One clarification. So I understand that your equations are not really fluid mechanics, because they also consider, I mean, there are some modification of the Navier-Stokes equations, perhaps large modification. But is there a term that plays a role of viscosity in these equations, or it would arise if you consider first 1/d correction?
Okay, so let me be very precise as to what the difference is between these equations and hydrodynamics. Okay, so if you take conformal relativistic hydrodynamics and you take the large D limit of that, and then you scale some of the transport coefficients in a particular way in 1/d, then you get what I have here. So essentially, so on the gravity side, you are already working with a microscopic theory. Okay, so your theory already knows how these transport coefficients scale with 1/d. And automatically on its own, when you're taking the first order in the 1/d expansion, you are sending an infinite number of those transport coefficients to 0.
Okay.
So effectively, these equations are second order conformal relativistic hydrodynamics with a particular way of taking the large D limit so that certain coefficients are taken to 0.
So shear viscosity, I mean, like naively one would say that eta over s equal 1/4 pi regardless of dimension, right? But this is probably too naive, right? Especially that no 1/4 pi appears in your equations.
You do have viscosity in these equations.
Okay.
Yeah, no, if that was the question, yes, you do have viscosity. So this is second order.
Okay. And how costly was the simulation that you done?
Or you can run it, well, it depends. If you want to run 256 simulations with very high precision, then you need to do a bit more work. And actually, we run the simulations on GPUs. But if you want to do a very simple simulation, one realization, you can do it in Mathematica in maybe 30 minutes.
Okay, super. Thanks.
No.
Any other question?
I have one more actually.
Yes.
So you showed us these plots where you have the forcing scale and then the Kolmogorov scaling to the left of the forcing scale and something else happening to the right of the forcing scale.
The direct cascade, you mean in...
Yeah, the direct cascade, that's right, to the right of the forcing scale. I was curious if that also made sense. Yeah, that's right. And you had an experimental plot of this as well, where it actually looked quite straight as well on the direct cascade side. I was wondering if that side also makes sense, or...
So I completely ignored it in this talk, and we didn't actually analyze it in the simulation. But you're right that we do seem to be getting a power law there.
Right.
And such a power law is to be expected in 2+1 turbulence phenomenology. And that is not related to having a constant kinetic energy transfer rate. There, the quantity that you're keeping constant is something else.
I see. Okay, so it's a different power according to the phenomenology.
Yeah, it's a different power. And so you can use, so here I followed this argument where I was keeping this kinetic energy transfer rate constant because that was the important scale for the inertial range that I was interested in. But if you have on the direct cascade in 2+1, then you have a different constant here with some different dimensions.
I see.
You can do a similar argument.
I see.
But the thing you keep constant is different.
I see. Okay, excellent. Thank you very much.
Any other comments, questions?
Can you hear me?
Yes.
Yeah, hi, Christiana.
Hi.
Roberto here. Yeah, I wonder whether you could characterize the forcing that you have using Mach numbers or Reynolds numbers to know which regimes you're actually probing, whether you're probing the compressibility of the fluid, or I don't know how you characterize the forcing. I mean, you had one forcing which is with vorticity, another one which is potential. But you could use, I mean, when you introduce this, I think it would be interesting to have some more precise quantitative characterization of the forcing. I'm not sure whether you did that in your paper.
No, we didn't.
Okay.
So we just use we solved things on the torus. So we had the length of the grid in the 2 dimensions, and essentially by playing with that length, we guaranteed that we had a large enough Reynolds number in order to be in the turbulent regime. But we didn't characterize the forcing term in any other way.
Okay. Okay, thanks.
Sorry.
That's okay.
But I think that just looking at your simulations, it looks like your velocities are subsonic, right? You don't excite, you don't have shock waves.
No, we don't. And we are happy for that, because then we would have had to do some more complicated numerics.
Sure, but I mean, once it's subsonic, then it's likely that you're, I mean, going to Roberto's question, it's likely that you're probing the incompressible region.
I think that is probably right. But how close? I think Roberto's question was, how close are you actually to the incompressible?
Well, once the speed is relatively small compared to the speed of sound, you're in the incompressible regime. So the corrections, so if you take that parameter to 0, you're in the incompressible regime. And then if that parameter is not of order 1, you're going to be you're going to be very close to the incompressible regime.
Okay.
Any final question? Okay, well, if not, then let's thank Christiana again.
Thank you.